Day, and I'm going to be talking about.
You forgot something.
I'm going to be talking about cupping with random sets, and this is joint work with Joseph Miller. Sure.
Okay, so Adam Day.
So if you want to come closer forward, if you can't see clearly from the back, you're welcome to do so. So where to start? I could start anywhere, but I'm going to start with a theorem of Gach and Kuchera that any
Peter is complaining already.
any Turing degree greater than or equal to zero jump contains a monolith random. So this is a, I guess, seminal result, and it's influenced a lot of how we thought about randoms and looking at the power of randoms, and also has sort of I guess the theorem itself is an example of being able to encode information into a random set. Now there is, I guess, an obvious intuition that things which are powerful are not random in some sense, and as we increase the level of randomness, then we find that you do not find randoms above zero jump. So I want to talk a little bit about the idea of coding, and the question is about, I guess, coding into Martin-Lev randoms that are incomplete. That is, they are not above zero jump. So the question I'm interested in Jez Kuchera in 2004 is for which sets A does there exist some, I guess, incomplete Martin-Lev random such that A join R is Turing above zero jump? And this question can be phrased in different ways, or you can look about things being equal to zero jump. But I just want to look at the basic form of the question. Now there's a relationship here to a theorem in computability theory by Posner and Robinson, which says that any non-zero degree below zero jump, you can find a one generic that joins this A up to zero jump. So maybe it's a diagram. Zero jump, for all degrees A, there exists some degree B, and which contains one generic. So what this question is asking, in a sense, is when you move from the case of be a category to the case of measure, do you get similar results or different results? Now, so not only did Kuchera ask this question, he also conjectured an answer. And the answer conjectured was exactly the not k-trivials, or non-k-trivials. So certainly, I guess today I'm going to present a proof that Kuchera's conjecture is correct. And what's lovely about this proof is that it uses, I guess, results from many people in this room that have been developed in the intervening 8 years and puts them together, and I guess validates in some sense a lot of the directions that people have gone into research, but also indicates that Couture must have had some quite significant intuition to conjecture that this was correct. In fact, this is conjecture which is an if and only if conjecture. It's not as if there was one result of the theorem and you're conjecturing it's tight. It's a kind of, it might initially appear as a stab in the dark, but I guess because it clearly wasn't. So there are
Other.
yes.
What means incomplete?
So by incomplete, I mean not above zero jump. So the random itself can't compute zero jump, but once you combine it with A, it becomes above zero jump. So there's one concept that I want to introduce, which is going to be useful in both directions of the proof, and it's a familiar concept, but let me just state it over here, so it's kind of, I don't erase it. So given some tau finite string, and some set p measurable, I talk about the density of tau in p, which is the measure of tau intersect p over the measure of tau, which is essentially just the conditional probability that p is going to happen given tau. So the idea is that we have some string tau in here, and we have some bits of p, and we really want to know that if we were just concerned about this cone above tau, what's the likelihood that an extension above this will be in p? And there's a definition. So we say, space here, x has lower density 0 in p if the limit of the density of its initial segments in p equals 0. So essentially we have this x in here, and as we look along the initial segments of x and we look at the conditional probability of p given that initial segment, it can get arbitrarily small. So why am I particularly interested in this concept? It's because of a couple of theorems which really explain, or I guess throw a lot of light on, exactly what these incomplete Martin-Liff randoms are. So here's two theorems. X is Martin-Liff random, and X is incomplete, i.e. not above zero jump, if and only if X is difference random and this is due to Franklin and Kingning-Ng. And I won't define difference random as, but basically it's a concept of randomness using difference of CU sets for tests. And then building on that result, there's this second result of Bienvenue, Herzl, Miller, Nies, that X is Martin-Liff random, and there exists some P, pi01 class, such that X has lower density 0 in P. So what's, I guess, significant about this result is that you have a single pi01 class that witnesses the fact that something is Martin-Left random and not above zero jump. And it's being able to move to the single pi01 class and this equivalence that allows to get one direction of this theorem. So this is one direction. If A is k-trivial, R is Martin-Left random, and A join R is Turing above zero jump, this implies essentially that A is unimportant. R is above zero jump all by itself. So hopefully you can see how this answers one half of the conjecture for things which are k-trivial. It's not possible to find an incomplete Martin-Left random that takes above zero jump. If you could do it with any random, that random itself must already be above zero jump. Okay, so here's how the proof goes. A join R is Turing above A jump. Why? Because A is k-trivial, and so A is low. I guess I'm not sure if that's Nice. And so then A join R is Turing above A jump. Also, R is Martin-Left random. A is k-trivial, which means it's low for Martin-Left randomness, which means A is Martin-Left random relative to A. So we have this result here relativized to, was a question or? We have this result here relativized to A. So X is Martin-Left random relative to A, and R is Martin-Left random relative to A, and R relative to A is above A jump. So we can show that it implies this result here relative to A. So there exists P, I'll use P sub A, pi 0, 1 in A, such that R is an element of P sub A and has lower density 0. Okay, let W sub A be prefix free such that I guess, so I want something which defines the complement of this pi 0, 1 class. So it's pi 0, 1 class, its complement is defined by a set of strings which is computably enumerable in A. Let WA be this. Now one of the things about WA is because A is k-trivial and WA is prefix free, so that means that WA has bounded weight. If I take the sum of all the elements of A, so the sum of sigma in WA, 2 to the minus length of sigma, is less than, well, it's less than 1, which means it's clearly less than infinity. Now there's a theorem which was, I guess, implicit in Miller, Kelsey-Hansen, and Solomon, but I think first published in more generality in a paper of Simpson, which says if you have this case, you can, and A is k-trivial, you can find a CE set which is a superset of WA and still has this property. So we're going to apply this theorem. Take So it's important that W is a superset as a set of strings go. It's not a well, which implies it's a superset in terms of the set of paths through it. But I'm actually just thinking it as strictly as a superset of strings, such that W is CE and the sum sigma in W 2 to minus sigma. Let's push this up. So this is I'm using this theorem and this fact about K trivialities to find a CE superset of the C's in A set. Now, of course, one thing I knew about my original set, WA, was that my set R was not a path in WA. R was in PA, so it couldn't be in WA. Now that I've added some things to WA to form a new set W, it's quite possible that I'm covering R. But because it's bounded, it's a Solvay test. And as it's a Solvay test, there can only be finitely many strings in this Solvay test that cover R. So I may as well just assume that R is not covered by W. So almost there in this direction. So what happens if I look at the complement of this? If I look at P, sorry, not P, I define P to equal the complement of this. P is a pi 0, 1 class. R is an element of P. And R, because this is even when I remove these things of R, this is essentially a superset of WA. R has lower density 0 in P. Okay, but now I look back over here and I find I have met all the requirements of this bottom side. Now, not relative to A, but just relative to 0. And so I can assume that because I was Martin-Left random, that I was actually Turing above 0 jump. Well, this is a mistake, yeah. The third one was, yeah, thank you. Not. So no, so it not shouldn't be there. X is Martin-Left random, and it's not there exists. Thank you. Yeah. So you can't. Yeah. So if X is Martin-Left random and above 0 jump, then it's not difference random, and then the previous thing as written would be correct. But thank you. Okay. So now I have the other direction, and so I can show that, use this to show that R is Turing above 0 jump. And so really, as you see from this proof, it's very short and makes essential use of these results here. And I like the fact that that I think, in having talked to some people, that these were just results of looking at interesting problems and then seeing how that things of those tools developed by looking at some interesting areas have come back and answered an older question. Any questions on that part of the proof? Okay, so now I'm going to go and try prove the other direction. So I'm going to prove a slightly weaker version of the main statement, as it's easier to get across, and then sort of state what the more generalized version is. But to start with, I'm just going to look at sets which are below zero jump. So if A gets below zero jump and not k-trivial, then there exists R and Martin left random R is strictly below zero jump and I guess such that A join R is doing equivalent to zero jump. So there were some preliminary results along this line from these, and essentially they were looking at, for example, omega relative to A and looking at some properties to do with that. And so they were looking at something which was random relative to A and looking at once you put A back in together, what can you extract from that? So this approach is different. This approach is saying, I'm going to look for something which is not random relative to A, but is Martin left random. So I'm going to make direct use of the fact that it's not k-trivial in that sense. I can find something that I'm powerful enough to make not random. Now what can you know? What can you, if you are A and you have some R, which is not random relative to you, one thing you can do is you can look at the stages that R enters various levels of a test relative to A. You know R is going to go into all of them, so you can find out at which stage, using A, does R enter the nth level of the test. And the idea is to control that so it stays random relative to A for a long time and then enters a level of the test very late, and use that to compute a function which dominates the settling time of zero jump. So that's essentially the main argument, and it's a matter of trying to formalize that. So the proof will be an oracle construction, so that the proof will be done from zero jump. And then once I guess the details will become hopefully a little bit clearer as I go through. So I'm going to define a partial order to be a set of pairs tau q such that tau finite string q of pi 0 1 class, and such that the measure of tau intersect q is greater than 0. And I'll say that tau 0 comma q0 is refined by tau 1 q1 f tau 0 intersect q0 is a superset of tau 1 q1. So the idea here is that we can't quite do a finite extension argument. I mean, typically from zero jump, you might build a descending sequence of these things where you have the towers getting longer and longer, And you take the limit of the taus, and that gives you the set that you want to construct. Here we have also these randomness requirements. And so we add a set, pi01 class, and essentially we're only allowed to take extensions of tau naught that stay inside this class. It's a bit like Matthias forcing, I'm sure, and this has been used in other contexts as well. So we're going to build a zero-jump computable sequence tau naught q naught, finding tau 1 q1, and let r equal the union of tau i's. But one important property we're going to maintain of this sequence is we're going to keep some sort of computable bound of the density of tau naught and tau 0. And this is a crucial aspect of the proof. We're going to ensure that d of tau I qi is bounded above by, it's slightly less than 2 to the minus I, but that's the idea. So even though this is somehow non-uniform, I mean, it's all being done from zero jump, these facts are computable. And you'll see why that comes in a second. Okay, so let tau naught q naught, so this is the empty string, and I'm going to take the complement of the first level of a universal Martin-Löf test. So I have the density of tau naught and q naught is at least a half. So now using zero jump, I'm going to find something below this, and I'm going to list a whole bunch of nice properties that this should have. I want tau 1 to be an element of, so U3 is going to be the third level of the universal Martin-Löf test relative to A. I want I want tau 1 to be the first initial segment to appear in here. I don't want any proper initial segment of tau to appear in this test. I want the density of tau 1, it's not quite true, I'll keep q naught the same at first, q naught to be greater than a quarter, and finally while I want to achieve this ultimately, I don't want to achieve it too soon. So I would like, when I get to some certain stage, which is going to be the settling time of the first bit of zero jump, I want tau1 to still be in U3. So I'm going to use the fact that I can extract tau1 in order to code the first bit of zero jump. So the modulus function okay, so assume I can do that successfully. I'll get into just like an outline of why that can be done later. What do I want to do in my next stage? I'm going to refine to some tau2. I'll leave tau1 the same, refine to Q1. Now, I also need to ensure that the thing that I'm building is incomplete. So at this point, I'm going to focus on making sure that no path through Q1 can compute zero jump via some functional. So say via the first Turing functional. Now the reason that I can do this is because by Sachs's theorem, the measure of a set of things that compute a non-computable set is 0, and I've got zero jump, and zero jump's powerful enough to be able to look for an initial segment of itself that a very small percentage of things compute, and just throw that out of Q1. So notice that this step, for determining the index of the pi01 class from Q1 from Q0 is something which zero jump is doing. It's certainly non-computable. Okay, let's just go one more step just to kind of clarify how that first step works again. Okay, so now I want to refine again, and I'm going to keep Q1 the same, but I'll refine to some tau2. I should have mentioned up here that it's easy to ensure that the density of tau1 inside Q1 is above, say, an eighth. So again, zero jump is powerful enough to throw out as little of the pi01 class that it wants. So now I want sort of tau2 to go into some level of a test. Just say k, because I don't want to give a complicated function, but it's computable in the length of tau1. And I want tau2 to go in late, so I don't want it to be in this test at stage m1. And I want it to be the first. Again, no proper initial segment enters earlier. I want the measure of d tau2 and Q1 to be greater than 1/16. So it's important that k is computable from the length of tau1 and sort of a stage of construction. So essentially, why should that be true? Well, if I know how long tau1 is, and I know the density of Q1 and tau1, then I know the absolute an absolute lower bound on the measure of tau1 intersect Q1, and so I just choose k large enough so that it will ensure that this level of a test must intersect with that part. Okay, so let me, maybe things will become clear once I explain how from A join R you can recover zero jump. So from A join R, I claim you can recover the sequence tau naught, tau 1, tau 2. I don't claim anything about the queues. So the first one is easy. This is equal to the empty string. Now given tau I, we know the density of, well, we can compute the k from the length of tau I plus I. And by k, I mean this particular component of the test. And then all I do is I just wait until I see some initial segment of R into that test. And as soon as I see some initial segment of R into that test, that is my next tau. Because as I wrote up at the top, no initial segment appears earlier, so you know you get the correct one. So tau I plus 1 first initial segment of R entering UK A at UK, the universal test relative to A. So I can recover R, so I can recover the sequence, and also I know from the time that these things enter the tests, I can take a function which dominates this modulus function. So I can compute zero jump by dominating the modulus function. How do you spell modulus? Okay, so essentially that's the idea. You try and maintain. Now the reason I had to try and maintain these densities to be bounded is because I needed, that gives me computing k from the length of tau and the I. The I tells me what percentage of the things above tau remain in the test. So that keeping this bound here computable was essential to the overall argument. But it's not at the moment clear that this step here, where you can actually find such an extension. So I want to just give a sense of why that's true, at least. So the key lemma would be the following. So I'm starting with some condition, tau q, and I know that the density of tau in q is greater than delta, and I have some values s, and given s, and so what do I want to show? I want to show there is some tau hat extending tau, so that the density of tau hat in Q doesn't drop too much. It's greater than delta over 2, and tau hat is in UKA. And tau hat is not an element of UKA for some fixed stage S. So S is a function, it's a value that we want to do better than N. So I mean S is equivalent to, M1. Now essentially the main work proving this lemma comes from a theorem of Kachira. Q is a pi01 class. Let's make sure I get this correct. This one. A positive measure then Q contains a tail of any Martin-Left random. So by a tail I mean if I'm given some Martin-Left random x, then I can just chop off some initial segment of that, and that's called a tail. So for any Martin-Left random x, you can move it into a pi01 class of positive measure by chopping off some initial segment of it. So what's the simple corollary of this? Q is a set of Here is a pi01 class of positive measure. And P, a set of A randoms and A is not K-trivial. Then Q is not contained in P. So the idea, if Q was contained in P, then if you took anything which was Martin-Left random, you could shift that Martin-Left random into Q by chopping off an initial segment. And if it was contained in P, then that would be A random. And so then any Martin-Left random which would have a tail, which is A random, which would imply that it's A random itself. And hence, you would have the class of Martin-Left randoms equals the class of Martin-Left randoms relative to A. So the proof show implies So essentially, it's just this idea is used to obtain this lemma. The idea is that you want to find some A that comes outside of that's not a random, and you want to stay inside, I guess, inside this Q, but then fall out. Oh, sorry, but then enter a level of a test, and I said, and I don't think it's necessary for the corollary, because it just requires that it contains only A randoms. But yeah, but it is. But that's what I'm using it for here. And I don't want to go through like the finer details, but essentially that's the idea: is that you can't force a pi01 class of positive measure inside a pi01 class that contains only A randoms if A is not k-trivial. You have to do a little bit more work to get the density being right, but essentially that's not too difficult to achieve. Okay, so that's I guess the main idea in this construction is you build a random, which is Martin left random, not Martin left random relative to A. You control the stages that it falls out of the universal test relative to A to compute zero jump, and you essentially prove some lemmas to show you can do that. So what's interesting now is that now given A join R, you can now compute this construction. And so you can actually determine what these pi01 classes are used to being. Now that's actually useful if you want to push this up and to be able to compute, to join up higher to different things. Because now, instead of just taking one possible extension, say from tau 1 to tau 2, we take two possible options, a tau 2A and a tau 2B. And we can now code by choosing which one of those two possible options we want to take. So this allows us to reach up further. So let me just state, I guess, the kind of the full result. Okay, so if A is not k-trivial, D is not computable, there exists R is incomplete Martin left random such that A join R is equivalent to A join zero jump join D. R is not Turing above D, and R jump. So I'll draw a picture, it might help. Here's 0. Here's some A, not k-trivial. I guess here's zero jump. A is not necessarily below it. I've got some other D over here, and they all, I guess, join up to this degree. I can find some R D that joins this, such that A join R comes up to the same spot, but R doesn't compute D. So the main idea in that is using coding. It actually becomes a little bit more difficult if, for example, D is not below zero jump, because you have to, at this point, now code R, so say code D, into the construction without coding it into R. And you get into a bit more of a difficult analysis of exactly why that works. It's also the interesting thing about keeping the jump. So this is essentially the degree of the construction, and you wanted to keep the jump of R below the degree of the construction. I guess one of the things that the Posner-Robertson theorem has been useful for has been precisely that property. You add something that jump is below it. So that's a nice, I guess thing to have. So just to finish with, I'll just mention one remaining question. So Slayman and Steele extended the Posner-Robertson theorem to show that for any A, it exists a one generic which joins it after zero jump, but they form a minimal pair. Can you do something similar with this? Can you find some A, if A is not k-trivial, can you find an R which comes up here, and such that they form a minimal pair over zero? Well, the answer to that question is no, because Kuchera proved that any two delta 2 diagonally non-computable degrees are bounded in computable CE set. So if you start with A being, if you start with say zero jump and A being a DNR degree, then if you try and find a random coupling partner, it's going to bound something which is non-computable. However, perhaps if you remember George's picture from the other day, perhaps the better question is that you, I guess, kind of think of the k-trivials down here. Perhaps it's possible, perhaps the more natural generalization of Slayman and Steele would be, is it true that for any A there exists an R, such that A join R go up to zero jump, and anything below the both of them is k-trivial? And I don't know the answer to that. I think our techniques can be extended to show that you get everything below both of them infinitely often k-trivial, but there's a big difference between infinitely often k-trivial and k-trivial. So thank you.
One question from Mark?
In this last part, you're doing cone avoidance above D. That is, you're avoiding the Turing upward closure of D. And just, and it's analogous to the Posner-Robinson theorem. Now, because I think they also say something about avoiding a cone. Now, I have a slight generalization of Posner-Robinson where you avoid the Turing upward closure of a pi01 class.
Okay.
Do you think you can do that here? I don't see why not.
Maybe not easily. I mean, the avoiding D is difficult because when you have this, haven't got erased. You have to be very careful about how you use D in the construction, because at the end you're just left with A and R, and so the main idea to get D back again is that there's first some A and R, you compute zero jump, and then you can almost do every step in the construction except when you make use of D, and you only make use of D at very limited occasions, and you have to code your use of D in a way into R in a way that R can't kind of retrieve it. So I'm not, maybe it might not be simple to extend it, but maybe.
Yeah,
I haven't looked in it.
Let's take a speaker.